Welcome back to the deep dive. Today, we're diving into something pretty critical. It affects things like the planes you fly in, the bridges you cross. We're talking about computational material failure, and
Mhm.
specifically how we predict cracks in big 3D structures. Now, this isn't just about, faster computers. Predicting these things accurately, down to the millimeter, can literally be the difference between safety and, well, disaster. Our sources today look at a really cutting-edge technique. It's called PFM-DSGM. It's a simulation method aiming to model how cracks grow in these massive structures. And the reason this is so important is because predicting crack growth in 3D is incredibly tough computationally. The shapes are complex, the physics tricky. Traditional methods often just, well, they bog down supercomputers. So we're going to unpack how this new approach, this PMDS-GFEM, manages to get the speed and stability that older methods just couldn't handle. Apparently delivering performance, what, 3 times better than the standard.
That's the claim, yeah. And our mission today for you listening is to really walk through why that is. We'll look at the trade-offs involved in the, let's say, traditional ways of doing things. And then we'll see how these new ideas, these enrichment functions and modification tricks, really deliver that boost.
Yeah.
We want you to understand how engineers are building tools that are robust, meaning reliable. They don't just crash and accurate, because that accuracy is vital when you're talking about major infrastructure.
Okay, sounds good. Let's start with the basics then. The workhorse, the finite element method, FEM, it's everywhere, right? Super flexible. But when you throw a crack into the mix, standard FEM hits a wall. It's all about the mesh, isn't it?
Exactly. The mesh is the grid the computer uses to break down the structure. And with standard FEM for fracture mechanics, what we call LEFM, you've got two big mesh headaches. First, that mesh has to physically match the crack surface geometry. If your crack is curving around in 3D, which they often do, just building that conforming mesh is a huge task.
Okay, so mapping it out is hard. What's the second headache?
The second one is the physics killer. Right at the very edge of the crack front, the math predicts infinite stress. It's a singularity. Yeah,
Singularity, right. Like the stress theoretically goes off the charts at that tiny point.
precisely. And to capture that behavior correctly, your mesh needs incredibly fine detail, super high resolution, right there at the crack front.
Okay, so you need a super fine mesh there. But what if the crack moves, which is kind of the whole point of predicting crack growth?
That's the nightmare. If the crack propagates even a little bit, your old mesh is useless because the singularity moved. You have to stop, throw it out, and generate a whole new mesh that conforms to the new crack shape and has high resolution at the new crack front.
Ah, constant remeshing. I can see how that would just eat up time and computing power.
Immense amounts. It makes simulating complex 3D crack growth incredibly slow and expensive, sometimes
Yeah.
just completely impractical.
Okay, so engineers needed a way around this remeshing problem, a shortcut maybe. This brings us to the first big idea. GXF, the Generalized or Extended Finite Element Method.
Right, GXM was a major leap. It basically decouples the mesh from the crack. The core idea is the mesh doesn't need to physically follow the crack anymore.
How does it do that? Sounds a bit like magic.
Well, it's clever math. You take the standard FEM mathematical setup that's approximations-based, and you enhance it. You add special enrichment functions.
Enrichment functions, okay.
Yeah, these are functions that already sort of know about the crack behavior. You add one type, usually a discontinuous function like the heaviside function, to represent the jump, the split in the material across the crack faces.
Okay, so that handles the discontinuity.
Exactly. And then you add another type, singular functions or branch functions, which are specifically designed to mimic that sharp stress concentration, that 12-col behavior right near the crack front.
So the GXFM approach lets you use meshes that don't conform. You just tell the math, hey, there's a jump here and there's a stress spike here using these special functions. Sounds brilliant. Problem solved.
Almost. It solves the meshing issue, and it can be very accurate.
Hmm.
But, and this is a huge but, it introduces a serious problem with computational stability.
Stability. Okay, what goes wrong?
What goes wrong is measured by something called the scaled condition number. Think of your simulation as solving a giant set of equations, represented by a stiffness matrix. This matrix holds the whole model together, mathematically speaking.
Right.
With GXFEM, especially using certain enrichment strategies, this condition number can grow much faster than with standard FEM as you refine the mesh. The matrix becomes ill-conditioned.
Ill-conditioned, meaning unreliable.
Extremely unreliable. It means tiny errors like computer round-off errors get massively amplified. Your solution can become complete garbage, or the simulation might just, crash entirely. It blows up.
Okay, so we traded the geometric nightmare of remeshing for a mathematical nightmare of instability. We just shifted the problem.
In a way, yes, GXM was a fantastic idea, but this stability issue really held it back for complex, practical problems.
Which brings us finally to this newer method, PFDSGFM. How does it tackle that instability problem while keeping the benefits of not needing a conforming mesh?
Right, this is where the real breakthrough happens. The PFDSGF framework, first off, it's built on a different kind of FEM basis, a hierarchical basis. Think higher order, smoother approximations within each mesh element. But critically, it introduces two specific mechanisms to wrestle that condition number back under control.
Okay, what's the first mechanism?
The first is called enrichment modification. They cleverly adjust those singular enrichment functions, the ones capturing the stress spike, using something called a discontinuous finite element interpolant.
Modifying the enrichment, does that hurt the accuracy?
That's the key. It's designed to be space-preserving. It controls the condition number, keeping it stable, without significantly damaging the accuracy of the solution you're trying to capture. It tames the instability without throwing out the baby with the bathwater, so to speak.
Okay, smart modification. What's the second stability strategy?
The second tackles a specific weakness in XFEM related to robustness. It happens when the crack path passes really close to a mesh node. This can split the node's area of influence, its support, into wildly uneven pieces, which again causes instability.
Ah, like an edge case that breaks the system.
Exactly. And the fix is quite direct. The node snapping algorithm.
Node snapping. You just move the nodes. Doesn't that mess up the mesh?
It sounds a bit brute force, but it's a local correction. If a node is detected as being too close to the crack, they use a tolerance of 5% in the studies. The algorithm just moves that specific node onto the crack surface.
Huh.
It prevents those badly split support regions locally, restoring stability. Because it's very localized, it doesn't really distort the overall mesh quality away from that immediate crack front area. It's quite an elegant fix for a tricky problem.
So you combine this careful enrichment modification with this node snapping trick. What's the result for stability?
The result is you get the best of both worlds. The PFM-DSGFM, with these strategies implemented, achieves a scaled condition number that behaves like 2. Now, that notation just means its stability scales the same way as good old standard FEM, which is known to be stable.
Got it. So it's mesh independent, like GXFEM, but stable like standard FEM.
Precisely. You get accuracy and robustness. That's the goal.
Okay, stability solved. Now let's talk 3D complexity. Real-world cracks aren't simple straight lines. They curve, they twist. We get not just opening mode 1 or sliding mode 2, but also this tearing motion, right? Mode 3. How does PFEM-DSGM handle that?
That's the next critical piece, especially for 3D. Mode 3, that out-of-plane shear or tearing, is common with curved crack fronts. Your simulation tool has to be able to capture all 3 modes accurately. So the researchers developed specific tools for this within the Stable framework. They introduced 2 new sets of scalar enrichment functions based on the Duarte or OD approach.
Scalar functions. Why scalar?
Mainly for ease of implementation. Older versions used vector functions, which were, well, complicated to code. These new scalar versions are simpler, but are designed to avoid problems older scalar versions had, like being sensitive to the crack's orientation in space.
Makes sense. And you said 2 sets, OD6 and OD9.
Right. The OD6 basis uses 6 of these singular enrichment functions. It's efficient and works great if you know beforehand that the mode 3 component is small or negligible in your problem.
And OD9.
The OD9 basis uses 9 functions. It's more comprehensive and absolutely necessary if you expect a significant mode 3 component. This happens a lot, for example, when the crack front isn't nicely aligned with the main axis of the structure or the loading.
Okay, so you need to choose the right tool for the job.
Yeah.
What happens if you, say, use the simpler OD6 when you actually have a lot of mode 3 tearing going on? How much does it matter?
Oh, it matters hugely. They tested this explicitly with a problem called the inclined elliptical crack, designed specifically to generate strong mode 3 effects. When they used the proper tool, the OD9 basis, they got a decent convergence rate, about 1.5, approaching the theoretical 3 for this type of element. But when they used the simpler OD6 basis on that same problem, the convergence rate just tanked. It dropped to around 0.6.
Wow, so less than half the convergence rate? Meaning much slower calculations to get even close to an answer, and the answer might still be off.
Exactly. It really highlights that picking the right enrichment basis, the one that matches the underlying physics you expect, is absolutely critical for getting accurate and efficient results. They also showed that for a problem without mode 3, like a lens-shaped crack, both OD6 and OD9 worked equally well, showing OD9 wasn't needed there.
Okay, this is all coming together. We have stability, we have ways to handle complex 3D modes. Let's get to the bottom line. For the engineer listening, how much better is this PFM DSGFMES method in practice? What's the performance gain?
This is where it gets impressive. The convergence studies showed that this quadratic PFM DSGF method converges 3 times faster than the standard approach used in industry, which is typically quadratic quarter-point elements for capturing crack tips.
3 times faster. That's a significant speed up for these complex simulations.
It really is. Now, there was one interesting subtlety. When they used standard uniform meshes, the convergence rate wasn't quite hitting the theoretical maximum. It was more like 1.59 instead of the expected 2, relative to the cubic rate of the underlying element polynomials.
Why was that? Still missing something.
Yeah, it turns out the current OD and similar BB enrichment functions primarily capture that main 12 singularity. But in full 3D, there are also higher-order singular terms, like terms sometimes called shadow functions, that these enrichments don't fully represent.
So even this advanced method has limitations baked into the current functions. How did they get around that to achieve the best possible rate?
The solution was practical mesh design. Instead of uniform meshes, they used sequences of non-uniform meshes that were heavily refined specifically right near the crack front.
So targeted refinement.
Exactly. By focusing the mesh density where it's needed most, they were able to compensate for the limitations of the enrichment functions and actually recover the optimal convergence rate of 2.3. It shows the method has the potential, but you still need smart meshing strategies.
That's a fantastic journey through some pretty deep computational mechanics. So to recap for everyone, we saw how PFEM DSGM cleverly combines the mesh flexibility of GXM with the rock-solid stability of standard FEM, getting that crucial dollar conditioning. And the payoff is huge. A potential 3-fold speed increase for modeling these incredibly complex curved 3D cracks, which is vital for engineering safety and design.
That's the key takeaway. You should now have a much clearer picture of the state of the art in simulating these fractures, and crucially, why making sure your computational tools are both stable and accurate is just non-negotiable. Ultimately, it's about getting reliable stress intensity factors, or SIFs. Those are the numbers engineers actually use to predict failure.
Absolutely. The convergence rates are compelling evidence of the method's efficiency. But as the authors noted, there's still work to do, particularly on nailing down those local quantities accurately. So here's a final thought for you to ponder. For real engineering applications, getting those SEFs right along the entire complex 3D crack front is the ultimate prize. What extra computational horsepower, or perhaps even newer mathematical tricks, might be needed to really capture those tricky higher-order shadow functions accurately? And how close are we truly to simulating 3D fracture with near-perfect fidelity? Something to think about.